Now it takes some amount of energy to get the electrons off of the photosurface itself, but then they're traveling off of the photosurface with some amount of kinetic energy. That's this EK right here. This is the kinetic energy of the electrons once they've left the photosurface. To stop those electrons from making it all the way to the collecting plate, as I said, some potential difference of voltage was applied across between the plate and the photosurface. And that voltage is called the stopping voltage. And down here in this equation, we represent stopping voltage with a V subscript S. We're going to apply a stopping voltage that's going to be able to completely overcome the kinetic energy of the electrons, and that's what this expression down here is. The Vs, the stopping voltage, times the charge of the electron gives you the energy that it's going to take to stop the electrons. Now if we look down at our two graphs down here, we have two graphs because there are two different variables that are being graphed. The first variable that we're looking at on the left is the effect of intensity. So we're keeping the frequency the same but changing the intensity of the light. And our current here is on the y-axis, our voltage is on the x, and this is the voltage that's being applied across the plate. And so we're starting over here on the positive side, and notice that the current is going down. As we get negative, that's telling us that there's a negative charge on the collecting plate. And so you can see once it gets negative, that's where our slope really starts to drop down. And so as the negative charge on that collecting plate increases, you can see that the current that's going through the system decreases dramatically until we get to our stopping voltage. And once it gets to the stopping voltage, it stops completely. There's zero current. The interesting thing to note about this particular graph is that even though the two lines start at different Y values, the bright red one starts at a higher current, the dim red one starts at lower current, the rates at which those currents decrease are different, and so both currents with the same frequency but different intensities drop to zero at the exact same stopping voltage. So what that tells us is that the energy of the electrons in both situations is the exact same. The difference here when we change the intensity is the number of electrons. So the more intense the light, the brighter the light, the more electrons are being emitted from the photosurface, but they all have the exact same energy. Now if we look over here on the graph to the right, it's again current on the Y, voltage on the X, but here we have two light sources with identical intensities but different frequencies. So we have a blue bright light and we have a red bright light, and we start up here and they have the same current, but as we get into more and more negative charges on the collecting plate, so as the potential difference gets larger with the negative charge on the collecting plate, the red bright light current starts to drop much more quickly. And so even though they start with the same intensity, the red light drops to a current of zero, which means that no photoelectrons are reaching the collecting plate anymore at a much lower potential difference than the blue. And remember that blue light has a higher frequency, lower wavelength than red light. And so as the frequency goes up, the energy goes up. So again, this is everything else is the same except for the frequency, so the photosurface, all of that is the exact same. By keeping the intensity the same, we are keeping the number of photoelectrons emitted the same, but because the blue light doesn't drop to zero until a higher stopping voltage. That tells us that the electrons emitted when the blue light strikes the photosurface have a higher kinetic energy than those emitted when the red light strikes. So again, as the frequency of the light goes up, the kinetic energy of the photoelectrons goes up. Alright, so just to review and recap, number one here, the stopping voltage stays the same no matter what the intensity of the light source is. So the stopping voltage is directly related to the frequency, not the intensity. Okay, and that's what we're saying down here. The intensity of the light affects the number of electrons emitted, but not the energy. So the more intense the light, the more photoelectrons emitted, but they still all have the same energy. The energy of the electrons depends on the nature of the light, and by that we mean the frequency of the light. Higher frequency, shorter wavelength radiation ejects higher energy photoelectrons. Now, when Millikan was performing these experiments, he found that for a specific photosurface, it didn't start gradually at the lowest frequency and have that energy of the electrons build and build and build from the very beginning. He found that for each specific photosurface, there was a frequency of light at which the photoelectric effect began. There was some minimum frequency of light that had to be shown upon the surface for the photoelectric effect to occur. It didn't happen at any wavelength. And that wavelength, that minimum wavelength that had to be shown upon the surface, was called the critical frequency. Or sometimes you'll see it called the threshold frequency. And if we look at these graphs on the right, specifically this top one, we have a graph of kinetic energy versus frequency. And this kinetic energy on the y-axis is the kinetic energy of the photoelectrons. And so what you can see from the graph is there's a very direct relationship between frequency and photoelectric effect. We'll just say photoelectrons. As the frequency goes up, so does the kinetic energy of the photoelectrons. And we talked about that in the previous graphs. But what you should see here is that there is some point at which that frequency meets with the x-axis, and this is the critical frequency. At the critical frequency, the kinetic energy of the photoelectrons is zero. So that gives them just enough energy to be emitted or to be kicked off of the photosurface. Now, if we trace this back to the y-axis and we look at where it crosses the y-axis, this right here, this amount of basically negative energy, is the amount of energy it takes just to get the photoelectron off of the surface of the material. And this little symbol here is what we use for that, and it's called the work function. And we'll talk about that in a second. Okay, but the important idea here is that there is some minimum threshold frequency that must be met in order for electrons to be emitted off of the surface of the metal. After that, there's a very linear relationship between the increase in frequency and the increase in kinetic energy. Where this threshold frequency or critical frequency occurs is a function of the photosurface. So if we look at a comparison down here at the bottom between two separate photosurfaces, we'll see that the slope of the graph is identical. And so the photosurface 1 and photosurface 2, if we graph frequency versus kinetic energy, the two graphs are parallel. That means that the effect of frequency on kinetic energy is identical in each situation. The thing that's different is what that critical frequency is. And so on the blue graph, the critical frequency is higher. On the green graph, the critical frequency is lower. And what this means is that this energy here the amount of energy it takes to get the photoelectron off of the surface is different for each of the two metals. For the green line, the energy to get it off of the metal is smaller. For the blue line, it's larger. And with this, realize that if you have a light that's shining on it of, say, this frequency, notice that at this frequency the kinetic energy is below zero. That means that no photoelectrons are emitted. So you could shine light below the critical frequency on your photosurface for days, weeks, months, whatever. No electrons are going to be emitted. And this becomes important to some of the conclusions that are drawn. So to summarize the observations of the photoelectric effect, the intensity of the incident light, and incident just means the light that's being shown upon it, does not affect the energy, only the number of emitted electrons. The energy of the electrons depends on the frequency, and there's a certain minimum frequency that has to be met. And the third thing, which is kind of assumed maybe but not directly stated until here, is that the electrons are emitted immediately. As soon as the light is shown on it, if it's above the critical frequency, electrons are emitted. There's no time delay. There's no, well, let's sit around and wait for the electrons to absorb the light, anything like that. It's an instantaneous effect. If light that is at the critical frequency or greater is shown upon the photosurface, electrons are going to be emitted.